Right, so this question, space mission planned to remove a small boulder, mass 8.2 times 10 to the 3 kilograms from the surface of an asteroid, and we're told the gravitational field strength of the asteroid at its surface, and we're asked to calculate the weight. So this is just a GCSE question, really, where force is m times g. The m is 8.2 times 10 to the 3, and g is 1.77 times 10 to the negative 4. So multiply those two together, and we get 8.2 times 10 to the 3 times 1.77 times 10 to the negative 4 gives us 1.4514 newtons. So 1.26 fig makes sense. So 1.5 newtons, but I've shown my answer to a greater number of sig fig there. Explain why gravitational potential is always negative. This one's quite difficult to get unless you get the first marking point, which is that the potential is 0 at infinity. If you don't get this marking point, it then makes it very difficult to get the other one, because the other marking point is you stating that at all other points less than infinity, the potential is lower, therefore it ends up negative. So potential is lower at all other points as work needs to be done to move the mass from infinity. And a number of people were saying that, but without that first marking point, you're not really explaining why it's negative. Gravitational potential at the surface of the asteroid due to the asteroid's gravitational field. So this is a potential. The spacecraft has this math to remove the boulder to where it's negligible. Calculate the work done against the asteroid's gravitational field. So this one. So this one, we're asked to find the work done against the asteroid's gravitational field. Now, a number of you missed that it's the spacecraft and the boulder that are going to be moving. So spacecraft and the boulder. So the total mass is 1.8 times 10 to the 4 plus 8.2 times 10 to the 3. So that gives us the total mass. And then the work done is the potential multiplied by the mass. So that's 3.99 times 10 to the negative 2. Actually, that ends up being a positive potential because of how we're moving it. Multiplied by those two added together. There's only one mark. So we end up with 1,045 joules. So the boulder is placed in a circular orbit. Circular orbit is mentioned again. Show the period is given by t is the square root of 4 pi squared r cubed over gm. So we have that the force equals mv squared over r, which equals the gravitational force available. So that's fairly standard. Those m's cancel. One of the r's cancels, and we end up with v squareds gm over r. But we also know that v equals 2 pi r over t. So we end up with 4 pi squared r squared over t squared equals gm over r. We also know that t is 2 pi over omega, which we could have got that step from an expression with v, but I didn't go for that this time. So we end up with actually just checking back. I don't need this step. So I just need once I've got 2 pi r over t, I'm actually pretty much finished. So I just need to re-express this. So I end up with 4 pi squared r cubed over gm equals t squared. So t equals root 4 pi squared r cubed over gm. Okay, last bit. We've just done a show that, so it's likely we're going to be using this again. So the orbital period around the moon is 24 hours. So 24 times 3,600 seconds. The mass of the moon we're given as well, radius of the orbit. So we've got t equals the square root of 4 pi squared r cubed over gm. So t squared equals 4 pi squared r cubed over gm. So r cubed equals gm t squared over 4 pi squared. And then we'll substitute the values in. So 6.67 times 10 to the negative 11. Mass of the moon, 7.35 times 10 to the 22. Orbital period, 24 hours, so 86,400 seconds squared. You get that from this. And then over 4 pi squared. So do that calculation. I end up with 9.27 times 10 to the 20. But we need to cube root it. And we get 9.75 times 10 to the 6 meters. Okay, the last bit. These come up quite a lot. Until you hit an equipotential, you can do whatever you like. So you just need to get from K to the moon any way you like. And the easiest way is to probably go this way. Now, you have to cross the equipotential line at right angles. So something like that. Anything that is drawn where you go through each equipotential at right angles will be correct. And this was quite erratically done. Quite a number of you weren't quite sure how to do that, so you've clearly not seen this sort of question before.